Good morning, sir.
Morning. So are you able to see the screen?
Yes, sir.
Okay. So let me just have a quick
Yes, sir.
summary of what we have been doing, and then we'll come to today's class. So we started with this inner product space. We did it for the complex vector space, but it is similar properties are there for the real inner product space, except that there is no conjugate symmetric. It will be the symmetric one. This inner product space allows us to define norms. That means we can normalize our vectors. Not only that, we can have set of n non-zero orthogonal or orthonormal vectors which can act as basis for any n-dimensional vector space. We did matrix representation of the inner product with respect to certain basis. So whenever we are talking about matrix representation, then it is always with respect to some fixed basis. And we find that this inner product matrix has to be Hermitian and positive definite. For orthonormal basis, it's an identity matrix. Now, we also did matrix representation of component vector in terms of inner product, again in the orthonormal basis or orthogonal basis. Then we came up with this concept of the projection of a vector on set of vectors or the orthogonal component of vector to this set of vectors, such that these two concepts allow us to formulate Gram-Schmidt orthogonalization procedure, which is that we can write any set of linearly independent vectors in terms of orthogonal vectors or orthonormal vectors. And in the end, we try to figure out something related with Cauchy-Schwarz inequality. This inequality plays a very important role in several areas, including Heisenberg uncertainty principle, and allows us to even define direction cosine of theta, for example, for the real inner product spaces. So this is what we have been doing. So let's just try to start today's class by first just defining something. So once we have the inner product space defined, we can also define distance between two vectors since we have defined length. So we can define distance between two vectors u and v simply as u minus v, which is of course nothing but u minus v. In several cases, it is not only important to actually check uh, the absolute distance of a vector with respect to some basis, with respect to some origin, but several times we are interested in figuring out the distance between two places, and in those cases this distance definition comes handy. Okay, so this is just a definition, and of course it will help you solving some problems. What I wanted to start with is to give you now an idea of the notation which I am using and corresponding to the notation which you may have started using in your quantum mechanics class. Now, this is famous Dirac notation which I have written on the right side, and this is the mathematician's notation generally. So in general linear algebra book, either you will see a simple bracket or these triangle brackets with a comma in between. Whereas in the Dirac's case, you will find this. So I just make a correspondence and then you will be able to understand for all practical purposes, that is dealing with all the numericals, etc. These two notations are equivalent. It doesn't matter whether you are going to write for me with a space sign between u and v or with the comma sign. The rules remain same. It is just that the comma is replaced by this one. But what Dirac achieved by doing this was tremendous. Anyway, let me just tell you what are these two viewpoints which are basically similar in terms of all the calculations, but Dirac's bracket algebra is a little bit more advanced for use in quantum mechanics. Okay, so here I told you Uh, Let me know if I'm still audible because due to some reason my internet connection just dropped. Are
So
you
you're
able to
audible
hear?
now. So
Yes,
you're
sir, you
Yeah,
audible
are
now.
you're
audible.
audible, sir. Yeah, I just changed the connection, but okay, let me see for how long I will continue on this one. Let's just continue. So we have vectors. The two vectors belong to the same vector space. Whereas in the Dirac notation, we have this V of course belong to this vector space, and it's common to call this as ket. Now it's of course a vector. I mean, you can call it vector, you can call it ket. In the Dirac notation, we call it ket, and in fact that notation is borrowed in mathematics also. And in several books you will see that these vectors are written as kets. So this notation which we are using, that is ket, and we will show come soon on this. What Dirac does further, that when you are going to apply something like this, it is no longer a vector in the same space. What it says is something like this, that I can apply this kind of structure from the left on this vector or the ket, and the resultant is a complex number. So what it is says, that this particular quantity, it is applied on my vector to give me a complex number. Remember what happens here, we are simply saying that this builds a complex number. So something like u is applied on v. Now when I am saying u is applied on v, you can understand that it is something, some what we call as functional. What is the difference between functional and function? Can anybody tell me? So this functional, when applies on this ket which lies in the vector space, gives me a complex number. So anybody who will tell me the difference between function and functional?
A function would give us a number if we apply it, and a functional, we get another function itself.
Yeah, but in this case it is a number, right?
Yes,
So
sir.
functional is giving me a number. So let me just write down. A function generally gets applied on something what we call as the numbers. So even if x is a real variable or a complex variable, it is a number. Function gets applied on a number to give me another number. So this takes me to something like this, or what happens to functional like this if I change the argument to some other object. Let's say in this case, the object is our vector or a ket. So when I am going to apply f on a vector, no, this vector can be anything, right? It can be a matrix, it can be a polynomial, it can be anything. So when I am going to apply something on a vector instead of number, the resultant I am going to call that as the functional. So the definition would be, a functional gets applied on a vector or a mapping which takes a vector to this complex number space, whereas a function takes any number to this real or the complex number space. So that is the only difference. But it makes a difference because what we are claiming now, that this guy is a functional, so it lives somewhere. What kind of functional? The functional is of the type linear functional. So let me just correct it. So when I say linear functional, it just means that if I am going to apply this guy on alpha v plus beta w, then the resultant will be alpha of uv plus uw. So this is the kind of functional which this u is. In fact, it can be shown that collection of these guys, which I am calling as the functional, it also forms a vector space. Now, this is interesting. First, we call it a functional, and then we say it is a linear functional. Now, this has to, of course, be true in order to ensure that it matches all the properties of the complex inner product space. Now, once I say that, afterwards we claim that this functional actually makes a vector space in itself, and this vector space is what we call as the dual or adjoint vector space of these guys. So in summary, to every vector or ket, please mute it, please mute. To every ket or this vector, there exists another vector in another space, which we call as the dual space, such that we have this a complex number. So basically, Dirac gave an identity to the left side also. Just like an identity is there for the right hand side, that it's a vector in one of the vector space. So Dirac gave some sort of idea that corresponding to every ket, there exists another dual space or a vector space where lives my linear functional. So for every vector, there corresponds another one. And this space of another one or the dual one, that is what is called the dual space, or what we commonly call as the, one second, bra space. Okay, let me just write it down properly. So, so this guy corresponds to bra space. This guy corresponds to ket space. That is the reason why we call these now as kets. So that when the two joins together, then it forms what we call as bracket. Remember that the C goes basically in defining this line. So Dirac's bracket notation introduces another space, which we call as the dual space, which is such that for every vector which is lying in regular vector space, there exists a vector in the bra space. And when two of these meet together, it is going to form bracket, which we call as the complex number. Now, this is also called adjoint space. Why it is so? Because now for Dirac, now see the interesting terminology which Dirac introduces. When a vector, a general vector, is alpha 1, alpha 2, alpha n, is depicted or represented by a column vector in this ket space, the corresponding bra vector is represented by a row vector complex conjugate. So that is why the use of the word adjoint space as well. That now we can actually think of whenever you are applying this guy, which is a ket, you can always think about a column vector. Whenever you are thinking about this guy, which is a bra vector, you start thinking about a row vector. So you do not need to now think about column vectors for both of these, v and u, and you do not need to think about now multiplication component wise, because if you multiply 1 into n row vector with a column n cross 1 vector, you will get 1 cross 1, which is just a number. So Dirac came up with this terminology because for Dirac now it is easy to think of every time I am thinking about a quantity like this, I am thinking about a row vector, which is complex conjugate, and every time I am thinking about a ket vector, I am thinking about nothing but a column vector. So I do not need to put two at the equal footing, on the equal footing. So this is the ingenious idea which Dirac gave, and from then onwards, quantum mechanics book and mathematics book on the linear algebra have slight different notations. Of course, one notation difference which you might have already seen, you may have seen if you look at, for example, Shom series. In the mathematics book, if they write alpha u comma v, this is what they define as. Whereas in quantum mechanics or physics books and in our classes, when we define as this, which is basically identical as writing this, this is what is defined as alpha u comma v. So quantum mechanics, physics, we use this. Mathematicians in their linear algebra book use this. So be very clear, whichever book you are using, you are able to follow the notations. We consistently use the notation which is used in your quantum mechanics class so that you do not get confused between the two notations. Ultimately, it is just the notation and the definitions. One more thing, in the case of Dirac algebra, you can even put a quantity like this. Remember what we said, that we are making an inner product. Inner product is when we are putting a bra vector together with a cat vector. But I can also put a cat vector with a bra vector, and it is still going to give me something in Dirac's mechanics. And can anybody think of what the matrix representation of this guy would be?
It will be a square matrix.
Because a cat is represented by a column vector, which is n row into one column, and a bra vector is represented by a row vector 1 cross n. So what will be the resultant of this structure, which we define as the outer product?
N cross N.
Integer.
Right. So you will got something which is n cross n, and today we are going to see what are these n cross n kind of things. Maybe you have already introduced there in quantum mechanics class, but this is important so that you make a correspondence. In terms of mathematics, nothing changes for you. In terms of the concept behind it, Dirac's bracket algebra allow us to define quantities like outer product and something, so many other things. Since it is allowing us to write something like adjoint vector, so we have also started writing like this. If I take the adjoint of a vector, then I will get something like this. This is what the Dirac notation will allow us to do, because this is how this space of linear functionals are defined. So this was a small short discussion on this notation which I wanted to do before proceeding further. Questions?
Sir, regarding the functionals, does it mean that a functional changes the space of what we are applying to? Like in your example, we took a vector from vector space and changed it to a real field. So a functional changes the space.
Yeah. I mean, the mapping, whenever a mapping is defined, there is some function of that mapping, right? So whether it is a function, whether it is a functional, whether it is an operator, which we are going to do, there is some operation of this. So what this functional is doing, this functional is basically getting applied on the ket space. So I am applying this guy, this is my functional, on a ket vector, and the resultant is a complex number. So it is just a field, nothing else. So of course you go from the vector space to field of numbers, but that happens only if this guy in this vector space and this guy in this vector space, such that this functional gets applied on one of the vector. So that's pretty common, right, for functional to do, isn't it? What is not common
Yes,
is
sir.
that functional itself will make a vector space. Generally, when we talk about functions, whether they make the vector spaces or not, that's not clear. But already you know f of x, which is the continuous real valued function or continuous complex valued function, they also make the linear vector spaces, right? It is a function f, function of real numbers or complex numbers. They are also constituting linear vector spaces. So this is something similar, except that, I mean, a mathematician will have to think a lot in giving this kind of a structure, the functional kind of a structure, some sort of identity. A mathematician was saying that, okay, why to worry about these two spaces? Why to call these two as separate spaces? Why not just put both of them are at equal footing and say that there exists a function which will take two of those vectors and give me something what we call as a complex function. So that is just the approach, nothing beyond that for the time being. But Dirac approach allows you to construct so many other quantities. And Dirac approach you allows us to use the adjoint operator, adjoint of any operation. That can be done, I mean, easily and one can easily comprehend it. So Dirac structure allows you to utilize the concept more effectively in quantum mechanics. Okay, anybody else? So for now onwards, from now onwards, let me just write down and then say, this is the third thing which we are going to do now. We have taken care of linear vector spaces. We have taken care of inner product. And now the third thing we are going to talk about the linear transformation or a mapping. Why do we want to discuss that? First, remember we did our vector spaces because we wanted to explain linear principle of superposition in quantum mechanics. C1 psi1 plus C2 psi2 is still a solution of the non-relativistic Schrodinger equation. Then we did inner product because we wanted to define a quantity like xi star xi, which is nothing but the probability density. Now, we are going to introduce something what we call as the linear transformation. And the reason why we are going to define this, because in quantum mechanics, every observable, whatever observable we are going to make, those observables are replaced by operators. And those operators have to be somehow defined in this space, because these operators do what? As the name suggests, they operate on these vectors, the vectors like psi1, vector like u or v, and then they will do something on that. It may be a position operator. For example, if I want to measure position, so I replace it by position operator, I operate it on a cat, and then I should get some result which should be some number. This is what we want to do. So we will reach there as the time progresses. Okay, so let's just define linear transformation or a mapping. So the word operator is little bit restrictive as compared to linear transformation of mapping. So let me just say how. A linear transformation or a mapping basically is something very simple. So if you have two vector spaces, let's say V and W, and let's say there exists a vector U in this V, in this one vector space. So linear transformation of mapping basically allows me to map this vector on the application of this transformation with some other vectors which is lying in some other space. So simple words, L, which I am defining as a linear transformation, will take me from one vector space V to another vector space. So let me just write down L acting on U will give me W, where my U belongs to first vector space, my W belongs to second vector space. So linear transformation of map or the mapping does this. That is what the transformation or the mapping is. Simple, just like the function or the function. Now the question, what is meant by linear here? Why I am using the word linear? That means I am talking about some special kind of mapping. What that mapping is, that there are two principles that have to hold true. One is called additivity, and another is called homogeneity. This happens in all the linear word whenever the word linear comes. And again, it is something very simple, that if I am applying to Lu plus V, that means that I am applying this L to some vector which is sum of the two vectors. Remember, sum of the two vectors will still be in the same vector space. Then the result will be L of U plus L of V. So the similar result you will see on the right hand side. So it doesn't matter where am I adding and when am I applying. So whether I apply my linear transformation first and then add, which is on the right hand side, or whether I add the vectors in the first space and then apply the linear transformation on that. So that is word additivity, and the word homogeneity is basically where alpha belongs to a field. It can be real or complex. It's a number. So if I'm going to apply L on some scaled vector. Remember, this is the scalar multiplication. Then the sum, then the result will be that as if I am first doing the transformation and then scaling it on the other space. So the word linear basically takes care of these two ones. And again, I mean, you can of course think about writing it together. So alpha u plus beta v, alpha of L times u plus beta of L times v. This is how we define a linear transformation. So a transformation takes you from one space to another one, and a linear basically ensures that whether we are doing the vector addition or whether we are doing the scalar multiplication, that remains preserved. So it should not matter. The ordering should not matter whether we are doing the first transformation or the addition or the scale. Now, what is linear operator then? Linear transformation and mapping is this. Linear operator is a very restrictive branch of the linear transformation, which I am going to define by operator T, but all it means that it is going to take from the same space to same space. Okay, what does that mean? This means that I may have a vector u and I apply this T and this may become u prime. So T of u becomes u prime, where both u as well as u prime belong to the same vector space. So it is just that I do not talk about now different vector spaces. When we talk about the operators, operators keep us in the same vector space. So that is the only part. Other than the linear, everything else, the linear word for the linear operator is exactly what we wrote for the linear transformation. So questions here?
Sir?
Yes.
Sir, since using linear transformation, we are going from one vector space to another vector space. So both vector space are having same field or different field?
Oh, it can have different fields. It can have different structures. The one can be polynomial space, another can be matrix space. Anything and everything is possible. So the plus rule, which I am basically writing same on both the sides, that may be different. So there everything. I mean, W is a vector space in all the sense. So it has to qualify all the properties. V is a vector space in all the sense. It has to qualify. But V and W are two different things. So I can take a polynomial and I can convert it into matrix, something like this. Yeah.
So sir, when we are saying alpha belongs to field F, so which field is this?
Yeah, so when I am saying alpha and beta, so whatever alpha I am choosing here, so if I am using my complex field here, then I am going to use my complex numbers there also. If I am choosing my complex number, real number here, then I am going to have my real numbers there. So the property which has to meet is this. If my vectors are scaled by some number, which is a field, either a complex number or a real number, on my left hand side, which is vector v, then the same numbers should get multiplied and they'll give this. So the linearity portion, so first portion was transformation. Transformation portion doesn't care about anything. Linearity portion cares that if the number alpha and beta were complex numbers on the vector space, then on the right hand side also it has to be vector space. So linearity will require me that the fields will have to be same. You got the point?
Yes, sir.
Yeah. So in case if alpha beta were real, then here also I'm talking about real. But this is portion which is coming from my linearity. This is not coming from my operator portion. Operator was not operator was allowing me to go from one place to another space just like anything. And when we are talking about the operator, in any case, since we are restricting ourselves to a single vector space, so the field of course remains same. In this case, you are talking about if there is 3 tuple on left hand side, it is the 3 tuple on the right hand side as well. If it is polynomial on the left hand side, polynomial on the right hand side also. Yeah. Okay. So, I mean, with this introduction, let me just ask a question. So in order to see if you understand this linearity portion clearly. So let me take a simple vector from R square to R. Fine. And what is the definition of this? So let's say a U vector, this is R square, two-dimensional. So I can think about something like x1, x2, such that when this operator T acts on this U, which is just like saying T operator x2, then the result turns out to be x1, 0. So an operator takes me from two-dimensional to two-dimensional real field, xi's are all real, such that the operation results in x1, x2 to be x1, 0. Question, is this a linear operator? So the first questions which come, just like the way it comes in vector spaces and the inner product spaces, whether a particular operation or operator qualifies to be a linear operator. And how are you going to do? Proceed.
Yes, so it
Additivity and
satisfies linear.
homogeneity.
Linear
Okay,
operator.
so let's just define. Very good. So let's check the additivity. V is equal to y1, y2. So what will be my u plus v, since I didn't define any separate rules? So that means it will be, let's just keep the standard ones, x1 plus y1 and x2 plus y2. Okay, now individually put these rules and see what happens. So tu is given. What is tv? So T acting on y1, y2. Result will be
Y1
By
comma 0.
y1 comma 0.
y1 comma 0. So if I add tu plus tv, what will be the result? So x1 0 comma 0, y1 comma 0. So this will be x1 plus y1 0. Let's apply my t on this u plus v together, which is what we wrote there. So t acting on x1 plus y1, sorry, x2 plus y2. What will be the result here? Now when I am going to apply t on this structure,
X1 plus Y1 comma 0.
x1 plus y1 comma 0, and if you compare the two, they are equal, right? You can do the same, something similar for alpha tu as well. So alpha tu will be what? Alpha x1 0, which is equal to alpha x1 0. Now apply this t on alpha times u, which is equivalent to saying I am applying t on alpha x1, alpha y1. So alpha times u, vector has to be scaled. No, not y1. I'm using x2, sorry. So use the consistent notation. Okay, alpha x2, and the result will be alpha x1 comma 0. So now compare the two and you will see that this is also true. So both additivity and homogeneity, these conditions are met, and hence this particular operator qualifies to be a linear operator. So this guy qualifies to be a linear operator. By the way, can you tell me what kind of operation this is when I am taking t of u, this is t of x1, x2, and taking it to x1, 0?
sir, this is projection x.
This is a projection on x-axis, right? Absolutely right. So you can just play around. So maybe I will give you, but do it as the homework. So I will ask you first the operation. Okay, t of u, let's say acting on t x1, x2, and this guy gives me x1 minus x2. What kind of operation is this?
Sir, reflection about y-axis.
Reflection about y-axis or x-axis?
Sorry, sir, x-axis.
Okay, okay, what about this guy? Minus of x2 comma x1.
Reflection about Y-axis.
Look into it. So
No,
I
no,
have changed
no.
x2 to x1,
Uh-huh.
x1 to
X2
x2, and
also
then I've
changing.
done minus. So something else is also changing. So think about it. And let's just let me just quickly ask you this question. So let's say whether I write caret or not, please see that I mean, it's a very common practice to write operator with this caret or hat on top so that you can make it basically distinguishable from the physical observable. So what do I mean to say? If x is the quantity which you want to measure, then you say that there exists x operator. P is a quantity you want measure, you say P operator, and it's a I mean P operator in wave function space, in this position space. How do we write it?
So I minus iota h cot del over del x.
Okay, so this is what is there in the position space. Now, does anybody remember if I want to do the same in momentum space? This is what you have done in your undergraduate.
So
So
P will be all same
P
as
remains
P
same
and X
and
is
X
same.
become
Iota h cot del over del P.
right. So these things, I mean, which basically came there while you were working on the non-relativistic Schrodinger equation, they will come naturally in our linear algebra when we are going to formulate this mechanics completely. But anyway, the important point is that this caret or hat basically distinguishes it from the physical observable. People, I mean, different people have different habit. Some guys write x pH. So just say that this is the physical quantity which we want to measure. Why it is just the notation anyway. So x1, x2, a quick question. So x1, 1, something similar to previous example. This qualifies to be a linear operator or not?
No, sir.
No, sir, it won't.
And why would you say that?
Sir,
So it doesn't
homogeneity won't be satisfied.
What about additivity?
it won't satisfy it.
It won't satisfy as well.
So this guy won't qualify as a linear operator. Okay, so we will be restricting ourselves first to operators and then to linear operators. But please see that whatever we do, that can be used to do linear transformation as well. All we need to think about that we are going from one space to another. Maybe I go from r cube to r square or r square to r cube. Things like those are perfectly doable things. We restrict ourselves with these linear operators in the same vector space because we are going to ultimately formulate our quantum mechanics principles. Okay, two things which are very important. When I apply linear operator on zero vector, then the result is always a zero vector. So zero vector is mapped onto the zero vector. Even though this concept doesn't look that important for my linear operator, but the same concept happens that if there exists zero vector in my first vector space, then the linear transformation or the mapping will also transform it to the zero vector of the other space. So this is quite an interesting and important concept for going from one space to another space. But this condition can also be checked. At times you can just check whether the zero is mapped onto zero or not. For example, in this case, in the operator which I have given, if you put x1 equal to 0 and x2 is equal to 0, you will not get 0, 0, which means that this cannot qualify as the linear operator. And I mean, proof is simple. I mean, you take zero vector multiplied by alpha or something alpha times 0 times u vector, and you will be able to do it. I mean, I will just put this proof as the homework, a small one. But this is an important property. Okay. Now, identity operator is the simplest operator which I can think of. What does this guy do? That this guy u vector lying in a vector space, this operator applies on it, and the result will be the same. So this does nothing. Nothing vector. Okay. The identity vector is still a linear operator, and you can of course check that. That identity operator does nothing, and all the vectors remain same, and hence it will be linear. The interesting one, for example, the differential operator in, let's say, one-dimensional real continuous functions, which is the function space, or maybe in polynomial, any space. I mean, these are linear vector spaces. So this is the differential operator. Now, differential operator will do what? So D acting on, since it's a real continuous functions of polynomial, it will act on a vector, which is now a polynomial or a real function, and it will still keep me, in the same functional space, either polynomial or the continuous function space. So if I start with, let's say, x square, for example, and I take d of dx of that, of x square, what will I get? 2x. So this is in P2 space, and this guy is still in P2 space. So polynomial wise, it is still real continuous function, So for differential operator, check whether this differential operator qualifies to be a linear operator or not. Okay, it will keep me in the same space, fine. Whether it qualifies to be a linear operator or not. So what are you going to do? D acting on fx plus, let's say, gx. The result will be f prime x plus g prime x. So it will take care of the additivity, which is nothing but d of fx plus d of gx. You can similarly check the scaling property and you will say, okay, sir, yes, this qualifies to be a linear operator. Another one of the common one. Not so common, but very useful one. So this is J, which I call as the integral operator, since I reserved for my identity operation. So what about J acting on function space? So let me define it. A to B fx dx. So this guy will be a number, a real or a complex number. So which means that from the real space continuous functions, I am still in the real continuous function. From the polynomial, I am still in the polynomial space. So integral operators also qualify to be a linear operator on the spaces. So remember, the spaces which we are using, they are very important. So questions here. So there can be several linear operators.
Excuse me, sir.
Yes.
Sir, can you please repeat this differential operator part?
Yes. What portion do you want to ask?
That said, D operator is a one-dimensional real continuous function. That one.
Yeah, I mean, you can take any polynomial is a continuous. So x square, for example, this guy is a continuous function, right? This guy.
Yes, sir.
Whether this or polynomial, whatever space you choose. Now, if d of dx acts on this, it will always lower degree by 1, right?
Yes, sir.
Right. Now, polynomial space of Pn, how is it defined? Set of all polynomials.
Function.
Set of all polynomials of degree
n plus 1.
Yeah, but less than equal to or fixed degree. How the vector space is defined for the polynomials. So we did that when we were dealing with the linear vector spaces. That what is the polynomial space? Is it the one with the fixed degree n? In which case, of course, this cannot be true. But if it is about less than equal to n, then of course it is true. So when do collection of polynomials act as a linear vector space? Of fixed degree n or less than equal to n? Of degree less than equal to n?
Less than equal to.
Less than equal to n, and hence it is important to notice that both of these will have degree which is less than equal to n, right? Whatever the degree of the first one, the degree of this resultant is always going to be less than equal to this, and hence this will also, to x, which is the resultant, will also be in the same space. It is not going out of that space, right? You got the point?
Yes, sir. Yes, sir.
Okay. And then you can, but you need to
Yes, sir.
still check. This is about the vector spaces, but then you have to check the properties of this. So if you apply differential operator on this alpha fx, so alpha is any constant independent of x. Can you write down this as alpha of d fx? Can you? So homogeneity will work in this, and additivity will work here. So additivity is what I showed. So this is basically, you can always write the sum of the polynomials as d operator fx plus d operator gx, which is additivity, and d of alpha fx can always be written as alpha times d of fx, because alpha is independent of a differential operator d of dx. So wherever you have confusion, use d by dx. Why I am using d hat? Because I am defining my linear operator as something like this caret. Remember, it is just the way you define your momentum operator, minus I h cross del over del x. It's easier to understand in terms of the this, that I am talking about the linear additivity or the homogeneity property. Is it fine? Yes, no?
Yes, sir.
Matrix representation of the linear operator. Now, when I am talking about the matrix representation, what comes to your mind? First thing which has to come to the mind. I'm talking about matrix representation. How, when can I talk about a matrix representation of a vector? I have to have something.
When rotation is concerned.
No,
Mm,
please understand this. Matrix representation will come always with respect to fixed basis. Rotation in 3 dimension is just one operation which will be allowed as a linear operation. That's a absolutely allowed one. But matrix representation, I am telling you that basis has to come to mind. That with respect to fixed basis, you can define your vector as the component vector, just the components, but with respect to fixed basis. So first thing which has to come to mind is this. Now, tell me, if I apply T of U1, what is this guy? So I am applying my linear operator on first of the basis. So I have a set of bases. So of course it is something like V and F space. So what will be the resultant?
Some other vector in the
Same
which
vector
is given
space or
in the
some other
same
vector?
vector space u2 u3
Same
or
vector
something.
space. So if it is in the same vector space, so I can expand it in terms of the basis vectors, right? Because it's the basis. So I can write
Yes,
down
sir.
anyone. So I can write down, that means alpha 1 1 u1 plus alpha 1 2 u2 plus alpha 1 n un, which is nothing but the linear combination of the basis vector. So I can write down. What about T of U2? I can write down this as alpha 2 1 U1 plus alpha 2 2 U2 plus so on and so forth. What about this T of UN? Alpha N1. So if basically I take any of the vectors of this basis vector and I apply my linear operator, then since my vector remains in the same vector space, I can always expand it with respect to the basis of the same space. Makes a perfect sense. Now, which makes the matrix representation of my linear operator with respect to a fixed basis. So let me just call this basis as S. And this will be nothing but alpha 1 1, and please see the definition which I am going to use, alpha 1 2, which is basically used mostly, alpha 2 1, alpha 2 2, so on and so forth, alpha 2 n, and alpha n1, alpha n2, alpha nn. First, what is the dimension of this matrix?
N cross
N
n.
cross N.
N cross
N
N.
cross n cross n. So An abstract vector or a vector in a vector space is represented by a column vector of the dimension n cross 1. A linear operator in the same vector space is represented by an n cross n matrix. First thing to always remember, every time you see a structure like n cross n, it can qualify as a linear operator. Okay, so linear operators are always represented by n cross n in VNF space. Now, thing which is important to notice is that I am using, so alpha 1 1, which is my first component, and then this alpha 1 2, this guy goes for the second portion, which means if you look into it carefully, that my first column is nothing but the expansion of my TU1 with respect to my basis. Similarly, my second column is this. So the only thing which is important, which you should remember, it is for the sake of consistency. There are ways to define it even as the row vector and things can work, but then you cannot interchange in between. So you have to use one notation. The notation which I am using is the one which is commonly given in almost most of the books, where each of these column vectors correspond to the components of the vectors of the first one, second one, so on and so forth. In fact, it is very important to note that if I know the operation or the of my linear operator on the basis vector, then I know what will happen to any general vector also. Now, a general vector in this space can be written as what? Beta 1 u1 plus beta 2 u2 plus so on and so forth, beta n un, right? Now, if I want to know what will be the result of this guy, can somebody quickly tell me?
Sir, this will be beta 1 times T operator on U1 plus.
Right. So this will be very good. Beta 1 times T operator on U1 plus beta 2 times T operator. And how did I get it? Using the
Linearity property.
linearity property. Absolutely right. But see the important point. I only needed to know my TU1, TU2, TUN, and then I will be able to know what will be the operation of T on any generic vector. So by knowing the operation on the basis vectors, what my linear operator does to the basis vector, I can actually find out what happens to any general vector also. So I'll do a question pretty quickly, except that I want to do one more thing in this class, that this is what? Matrix representation of T in a given basis. This guy is what? Can somebody remind me what will be the dimension of this guy? This is a vector matrix representation in a given basis. So this was n cross n, and this is
N cross 1.
Rohit 1. It is same as doing this. So this is interesting property. And I just want to have a very quick one of this one. So V square, so it doesn't matter whether I take the matrix of T in this space and the matrix of V in this space, or I first apply this linear operator on V and then take the matrix. So very quick confirmation or the check of this one. So let's say we are into V2F and we have a set of two vectors u1 and u2. Fine. So how can I write my T of u1? This can be written as alpha 1 1 u1 plus alpha 1 2 u2, right? I mean, this is the basis vector. And what will be T of u2? This will be alpha of 2 1 u1 plus, so I keep my same notation same as my previous page. So can you quickly tell me what will be the
Alpha 1 1,
Alpha
alpha
1
1 2,
1.
alpha 2 1,
Alpha
alpha
1
2
1.
2.
So what should I write here?
Alpha 1 2.
Alpha 2
Alpha
1.
1 2. Then alpha 2 1 and alpha 2 2. Okay, fine, fine. Let me now just take any general vector in this one and define it as beta 1 u1 plus beta 2 u2. I am perfectly allowed to do it because this is a general vector in the same vector space. So how can I write this v of s? This will be
Beta 1,
Beta 1 and
beta
Beta
2.
1 1,
Beta 1 and
beta
beta 2.
1
and
2,
beta 2.
beta
It is a
2, beta
simple one, right? So let's now try to see what happens if I am applying t on this vector v. So I am applying t on this vector whole of this one, which is basically writing beta 1 t of u1, which is what we did in the previous page, beta 2 t of u2, right? Now, t of u1 we already got here and t of u2 we already got here. So let's just quickly do some mathematics, a simpler one. Alpha 1 1 u1 plus alpha 1 2 u2. In case if you are keeping your notebook ready, you can also do it, but okay, I mean, this is not a tough one. Okay, part 1. Part 2, just take the term of the type u1 together. So you will get alpha 1 1 beta 1 plus alpha 2 1 beta 2 times u1. So this is the first term from here, this is the first term from here, plus next one alpha 1 2 beta 1 plus alpha 2 2 beta 2 times u2. So which means that I can write down this guy, which is t vector t of v with respect to fixed basis. What is this one? So now I have got this term and this term. Quickly, this is another vector, so it should be replaced by, it should be represented by a component vector of 2 into 1 type.
Alpha 1 1 beta 1 plus alpha 1 2 2 1 beta 2.
Beta 1 plus alpha 2 1 beta 2, and this guy should be alpha 1
alpha
2
yes,
beta
sir.
1 plus alpha 2 2 beta 2, right? Now
Yes, sir.
do this multiplication of 1 and 2 individually. So now do this t of s, which is this guy. So you are doing what? Alpha 1 1, alpha 2 1, alpha 1 2 2 2 times beta 1 beta 2. So you should get what? Alpha 1 1 beta 1 plus alpha 2 1 beta 2 and alpha 1 2 beta 1 plus alpha 2 2 beta 2. Compare your result of 3 and 4. This is 3 and 4. What do you get? This important point. So we will start with the numerical in tomorrow's class to just cement on what we have done. That we have tried to see that if somehow we know the application of our linear operator on the basis vectors, then we know the application of the linear operator on any generic vector in that space. Because all we need to remember is the operation on this, and the linearity will allow us to do rest of the things. And one thing which goes nicely is that whether we get our two matrices and multiply it, or we apply our linear operator on this vector so that we are getting another vector and then writing the component directly, it is immaterial. Again, because of the linearity property, this thing is there. So whatever I have done for 2 by 2, this will be true for any n cross n matrix. Yeah. So question here, and then we are basically finishing it today. No questions? Then thank you, and we will continue tomorrow.
Thank you,
Okay.
sir.
There is a question? No? Yeah, raised hand. Pushpendra.
Thank you, sir.
Thank you, sir.
Thank you, guys. Pushpendra, do you have a question?
Thank you, sir. Thank you, sir.